So we looked at Bohr-Rutherford diagrams yesterday, and we learned that atoms are are electrically neutral particles where their electrons are equal to their protons. Okay, and the protons, if you remember or recall that protons and neutrons are located within the middle of the atom, and electrons are in orbits outside of the atom, outside of the nucleus of the atom. And you remember that electrons are equal to the number of protons, and that's what causes our atoms to be neutrally charged atoms. Okay, but that's not how atoms actually react to each other. In fact, the way atoms actually react to each other, okay, are because they can form these things called ions. And an ion is an atom or a group of atoms carrying an electrical charge. Okay, there are two types of atoms. The first one are cations, and the second one are anions. Cations has a T, so you can think of them as positively charged ions due to the release of electrons. Okay, so cations don't want to have these electrons. They say, you know what? I want to be positive. I hate being a negative atom. I will. No, it's not how it is. It says I just want to get rid of. I want to get rid of my electrons. Okay, so some sort of energy must be added to cause the release of electrons, and this can happen through a chemical reaction, through a combination of two ions. Okay, and we'll learn a little bit more about that. But what happens with a cation, okay, is that energy is added, and sodium's Bohr-Rutherford diagram looks like this, right? This is sodium's Bohr-Rutherford diagram with a neutral charge, okay? We can call this an unstable sodium or neutrally charged sodium atom. Okay, you have 11 protons in the middle, you have 11 electrons along the outside, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, okay? But there's that one atom, there's that one electron right up here where the sodium's like, no, I don't want this. I want to get rid of this. Okay, so energy is added, and what happens is sodium now loses an electron. Okay, and because you have 11 protons, and now you've lost that one electron, sodium now becomes plus one charge, right? So 11, this is not lined up. 11 minus 10 is plus 1. Okay, so is 1. Okay, so sodium now becomes Na plus 1. Okay, and that's the ion, the cation that sodium forms. Okay, we can also look at it in a way, or another way to explain that is, all these neutral atoms, they all want to try to gain a full, they all want to be noble gases. They all want to try to gain a full outer shell, electron shell. Okay, so if you compare sodium to neon, okay, neon has a full outer shell of 10 electrons, okay, 2 in the first shell, in the first orbital, and then 8 in the second orbital. And sodium's like, no, man, I want to be like neon. I want to have an electron configuration the same as neon. So sodium's like, in order for me to do that, I need to get rid of this one proton. It's easier for me to get rid of, one electron. It's easier for me to get rid of one electron than to gain 7 electrons, okay, to look like neon. So I want to get rid of this one electron, okay? And then once sodium gets rid of that one electron, okay, it now looks exactly like neon. It's like, hey, now I look like you. Neon, we're buddies now, okay? And it has a full outer shell. That's the goal of all neutrally charged atoms, is they want to look like noble gases. For some reason, um, atoms want to have a fully filled outer shell. Okay, and so sodium says, no, get rid of this one electron, and now I'm happy and I'm content, and I look like neon. I look like a noble gas. I'm nice and noble, and I'm more stable like this. Okay, so sodium then loses that one electron, and because there's still 11 protons and 10 electrons now, okay, you subtract 11 from 10, or sorry, 10 from 11, and now you're left with a positive 1 charge. You can put either a 1 right next to this, or you can leave it as Na plus. Okay, the reason why sodium doesn't lose, say, 2 electrons is because if it lost 2 electrons, it would no longer look like neon. Okay, and that's similar to all the alkali metals in the first group here, group 1 alkali metals. Okay, these ones easily form cations and are chemically very, very, very reactive. Why? Because it's super easy, okay, for them to just lose that one electron. Okay, it's just one electron. It's not like it's five electrons. It's one electron. So it's easy to pull out one electron as opposed to pulling out two electrons in group 2. Okay, or three electrons in group 13. Okay, so it's easier to do that as opposed to pulling out two or three. What happens is as you go down this group, okay, this alkali metal group, what happens is the reactivity actually increases as you go down. This is because the valence electrons get farther and farther and farther away from the nucleus, okay? And they're more loosely held, right? So you have one shell here, two shells in this row, three shells, four shells, five shells, six shells, and you just keep going down and you're increasing the size, the diameter of that Bohr-Rutherford diagram, right? If you picture that Bohr-Rutherford diagram, you're increasing the orbitals. And the farther and farther and farther and farther away that the electrons are from the nucleus, the positively charged protons, the easier it is to pull those electrons, so they become much more reactive, okay? The farther the valence, this is what I said, the farther the valence of an electron is from the positive nucleus, the more easily it is removed and the more reactive the atom is. Okay, so again, as you go down, the easier it is to remove, the more reactive it is. Group 2, or the alkali earth metals, are also form cations, but must lose two electrons. Okay, like I said, the alkali metals can lose one electron, which is really easy. Okay, the alkaline earth metals, they need to lose two electrons, which makes them a little bit less reactive than the group 1 alkali metals. Okay, they're less reactive than alkali metals because more energy is needed to remove two electrons than one, right? So pretend you're trying to grab, you know, a ball out of my hand. It's easier to grab the one ball out of my hand than trying to grab both balls at the same time out of my hand. Okay, you can think of it like that. I don't know if that helps or not. So magnesium, for example, okay, magnesium has 12 protons, 12 electrons. You have magnesium plus energy, okay, and then magnesium will actually lose two electrons, the two electrons, one electron here, two electrons here, okay, and you're left with magnesium 2 plus. The reason why we write the 2 here is because you need to tell me that it's a positive 2, okay, it has a charge of plus 2, okay, and the two electrons would be kind of left over here saying, you can go to fill another outer shell. Okay, now magnesium looks like a noble gas. Magnesium's happy, he looks good, he's noble, he's feeling good, or she's feeling good. They look like a noble king or queen, okay, and that's what they want to look like. Okay, but it's important to write that that script up here is 2 plus because you're telling me that it's lost two electrons as opposed to sodium, which only lost one electron. Okay, so you can look at here, neutral, this is unstable, okay, because it has these two extra, sorry, it has these two extra electrons here, so it's unstable, and now it is stable, okay, and you look at the Bohr-Rutherford diagram, 2 in the middle here, or 2 in the first shell, and then 8 in the second shell. Okay, aluminum, which is in group 13, okay, aluminum has 1, 2, 3 electrons in its outermost shell. Think about this. Is it easier for aluminum to gain 5 electrons or lose 3 electrons? Remember, aluminum and all atoms want to look like noble gases. They want to have full outer shells. So is it easier to gain 5 electrons or lose 3 electrons? Okay, yes, it's easier to lose 3 electrons than 5 electrons, right? Or than to gain 5 electrons. So aluminum will actually get rid of 3 electrons. And if you can picture where it is, aluminum is in group 13 right here, okay? It's right here and it wants to look like argon. Okay, so what happens is aluminum will lose those 3 electrons. And if you do the same math, you have, you lose 3 electrons, you become positive 3, right? There's going to be, there's 13 electrons in the unstable atom, okay, and 13 protons. And then with the stable atom, the noble gas looking atom, you're left with 13 protons minus 10 electrons, okay, and you're left with a positive 3 charge. Okay, I hope that makes a little sense, makes some sense to you. We're going to move on to anions now. Similar to cations, anions, okay, actually form negatively charged ions due to the gain of electrons. Okay, so they want to gain electrons instead of lose electrons. Cations lose electrons, okay, it become positively charged, where anions say, oh, I love electrons, electrons, come to me. Okay, and anions are negatively charged ions due to the gain of electrons, so they become negative, right? The more electrons you have in an atom, the more negative that atom becomes. Okay, so energy is released when this reaction, when an electron is gained. Okay, so you have fluorine, fluorine looking right here, you have 9 protons, 9 electrons, you have a 0 charge, it's a neutral atom, but it's unstable. Okay, because again, same thing with cations, these anions or these atoms all want to look like a noble gas. They want to have a full outer shell. So you think about it, is it easier for fluorine to lose 7 electrons or to just gain 1 electron? Okay, with the electron, it gains an electron, energy is released. Fluorine now has a full outer shell. Okay, it has 9 protons, 10 electrons, which gives it a -1 charge. Okay, and remember, it's gaining that electron, so energy is being released. Okay, as opposed to energy being used. Okay, and remember again, these atoms, these neutral atoms, fluorine, it wants to look like a noble gas. Okay, so right here you have fluorine has 1 extra electron. It's easier for it to gain another electron to look like neon. So it says, hey, you know what? I'll just take an electron from, say, sodium or from calcium. And what happens is that electron comes in. Okay, it now has a -1 charge and it looks and it's happy because it looks like neon, the noble gas. Okay, group 17 halogens easily form anions and are very reactive. Okay, similar to the alkali metals in group 1, okay, these ones, instead of getting rid of 1 electron, all they need is to gain 1 electron. And it's very easy for them to gain 1 electron because it's only 1, right? It's easier for me to take one thing as opposed to taking 2, 3, or 4 electrons, okay? But what happens is the opposite as to what happened in alkali metals. In in the halogen group, okay, what happens is the reactivity decreases down the group. Why? Because as you increase orbitals, okay, 1 orbit, or sorry, 2, 3 orbits, 4 orbits, 5 orbits, 6 orbits, what happens is you increase orbits, okay, you're getting farther and farther away from the nucleus. And what's in the nucleus? You have protons in the nucleus, and protons are positively charged. So the farther away you get from the nucleus, the less attraction those electrons have to the atom, okay, or to the atom in order to gain that electron. So as you go down, okay, it gets less and less reactive because of the diameter or the size of the actual atom itself. So reactivity decreases down the group as valence electrons get farther from the nucleus. Positive nucleus has less ability to attract gained electrons. The farther the valence electron is from the positive nucleus, the less easily it can gain electrons and the less reactive the atom is. Let's look at sulfur. Okay, so sulfur, what happens with sulfur? Again, sulfur wants to look like a noble gas. It wants to be nice and noble and have a full outer shell. So what happens with sulfur is you can count here that sulfur has 1, 2, 3, 4, 5, 6 electrons in its outer shell. And it says, yo, is it easier for me to get rid of 6 electrons and become positive, or is it easier for me to gain only 2 electrons to become negative? And of course, in order to look like a noble gas, it's easier to gain 2 electrons. So sulfur gains 2 electrons to get to an ion charge of -2, okay, because now there's 16 protons and 18 electrons. Okay, group 16 also forms anions, but must gain 2 electrons. Okay, must gain 2 electrons, and if you move one over here, must gain 3 electrons, group 15, okay, until it gets to a point where it's either easier to lose electrons than to gain electrons, as we saw in group 13 with aluminum, okay. They are less reactive than group 17 atoms. After the first electron is gained, the anion is already negatively charged, and because the similar charges repel each other, it just becomes less reactive. Okay, and this is another example of sulfur here. I'm going to start another screencast. I hope that made sense. If you have any questions, just let me know. And I'll start the second screencast as my time is running out here. And we'll start off right where this sulfur atom is. Thanks, guys.